Okay, recording is started. So I guess we'll see if people come in. And I'm open to the file, and happily the file has compiled, or has it compiled? 2593 out of 2595. So it's doing the weird thing where the orange bar has disappeared, and yet the info view is not quite there yet. But usually when that happens, the info view tends to get there within a few minutes. So I think that should be fine. Okay, and it's almost at the top of the hour. So, and the nice thing about YouTube streams is that you can like rewind and like watch it on a higher speed. So hopefully it's not an issue if I start explaining what I'm about to do. Okay. Right, so I'm open to the beta lean file. Okay, so what's the plan for today? The plan is to go, maybe I should just make a new file for this, I don't know exactly what to call this theorem, like LCM theorem, LCM Lower Bound. And I want it to import this, import MATLAB analysis special functions gamma beta, import MATLAB.analysis special function gamma. Okay, I want the beta one though. Info view still thinks it's on beta.lean. That's nice. Okay, so there's sort of a nice paper that has like very clean proof of the fact that I want to prove. But I did want to see if I could sort of just reconstruct and redo the whole proof from memory because it was a pretty short proof. Maybe I should like delete the info view and re-add the info view. So yeah, so that's still loading. Okay, so what are we proving here? Lower bound on the LCM of the set of numbers 1, 2 through n. And this is the part where it's always interesting to see. Yeah, that's correct. 2 to the n minus 1. Okay, well, that's not the thing that I heard. The thing that I heard is that it's at least 2 to the n, namely that, and this is only true for sufficiently large n, for n greater than 7. Okay, so it's smart enough to know that the number is 7. So clearly it's read something along these lines before. This is done, well, okay, so the proof that I saw was like a very clean proof that used the beta integral, right? Which was sort of hard to find. It was a little like hard to find that it was the name of this, but basically there's this particular integral, and it's okay. Here U and V are complex numbers, but in the proof that I saw, it was just integers or natural numbers. So to the beta integral. To the beta integral. And so like here's my like let me try and like recreate and summarize the proof. So the proof goes something like integral. How do you actually write? Yeah, how do you actually write the integral? Using \integral. Okay, I thought I was in the middle of typing that. Yeah, the integral from 0 to 1. Okay, this is like a hilarious integral, like lower 0, upper 1 of. Okay, so this is actually just. This seems like it's sort of recreating the proof that I saw, right? Basically, this is a beta integral. So that like the traditional beta integral is like so if I go to the beta function, right? If I like beta function maybe is Wikipedia, you can like see that it's sort of related to this. Yeah, I guess it's like related to the gamma function and related to binomial coefficients, but it's this function. And the nice thing about it is that it also has this form. Okay, so here it is for n and m, and I'm not sure that they're exactly the same n and m that I was looking at over here. But the idea is that it has this form of the integral. Like what is this integral? I sort of think of it, it's 0 at 0 and it's 0 at 1, and it's like one way of thinking of it is it's like the posterior distribution you get if you sample a bunch of if you like sample a bunch of things from a binomial distribution. I think that's one interpretation of it. So Yeah, so there's two facts about this integral that they use. Basically, the whole proof is something like, okay, so this LCM thing, right? Uh, I think you can like abbreviate it as LCMN, where we'll define this as LCMN, colon equals this LCM thing. And the point is that LCM of n is, so number one, LCM n like times the quantity of like fraction of, okay, so I'm like, clearly it's wanting to type a whole bunch of things for me, but 1 divided by m times choose like nm, yeah, is an integer for all 1 less than m less than n. Now, do I have this right, or is there like an off by 1 error here? So basically, the first part of the proof is just to like prove that this fact is true, um, for by basically like computing this integral in two different ways. And one way, it's clear that it's like always a multiple of LCM n, and so it's always an integer. And the other way is proving that it's basically just equivalent to this formula here. Um, and so I think it's probably true for like 0 as well. So you prove that it's an integer in this way. And then the next step of the proof, let me see if I recall. So basically this gives you some facts. Here, let me actually first like double check that all of my stuff is right by writing some lean code. Um, yes. I wonder if I can like do something like LCM natural number to natural number, because this, I want like the best way of doing this is maybe to like, um, 0, that would be like the empty set. And so I'm not sure if like the value for 0 might be a garbage value. But the point is that 1 should be 1, and then n plus 1, it should be the LCM of n plus 1 and the LCM of n. Yeah, so this is LCM n. So this is a way of computing this thing. And right, so the point is that, here, let me like see if I can write this as a lemma. The point is that LCM, it's a, like one way of saying this is that it's an integer, right? So what is another way of technically it's also like a positive integer. So what's the technical way of writing this? So LCM divides m times n choose m, or have I got that backwards? So clearly LCM is larger than, yeah, if that's going to be a positive integer. So I think the way of writing this is that, okay, so the theorem that I want to do is for m LCM, or let's see, choose, like let's try and come up with the proper MATLAB theorem name. So it'll be something like mul choose divides LCM. Yeah, so these are facts. Okay, it's a little weird that it like chooses to write it in that way, which is not the best way. The fact that I want, right, so the LCM is larger. So the fact that I want is something like m times n choose m divides LCM n. And this is the fact that I want to do. And in theory, I should be able to, okay, am I still like not, okay, MATLAB is still not working. So this is sort of unfortunate. So let me try and restart my server and see if that works. Okay, cool. So you've realized that your imports are out of date and they must be rebuilt. So I will press the restart file, which I've just done. Okay, cool, wonderful. And so, yeah, so this is true by sorry. But like this is like this sort of case where it's like, okay, if I'm like testing things out, it should be possible to use like plausible here, right? Gave up after failing to generate prediction values that fulfill the preconditions one time. You gave up after a single try. Okay, well that's a little lame, is it not? Nevertheless, we can always just we can always like check this manually, right? So like one way of doing it is like eval, and let's do like 10 times 20 dot choose 10 unexpected identifier. Can we not do, is this not allowed? Nat.choose, how does nat.choose look? Nat.choose, nk, yes. So nat.choose 2010, okay. Okay, well that's not the result that I wanted. So let me think about what is the actual, maybe I've messed up this fact here. Let me do some investigation. Right, LCM 20, like, first of all, let's eval LCM 20. Yeah, this seems like a very reasonable value for that to take. What happens if I do LCM 10 dot factorization or something? Okay, like prime factors. The problem, one issue is that it's that. Yeah, well, those are the okay. But how do I get them? One sort of issue is that I feel like it's would be much more appropriate the um, for the list of prime factors, right? There should be a function that gives you the multi-set of prime factors, but I guess we don't have that. Let me like look on Lugal or something. Okay, so I was just setting up this like at what I want is like the set of the list of prime factors of a natural prime factors list. Okay, well, clearly that's a wonderful name for such a thing. Let me see what the prime factors list is. Invalid field nat. Okay, well, cool. Clearly I need to delete this. Yeah, so 3 2s because 8 is less, 2 3s because we have 9, and then 5 and 7. Okay, so that looks like a correct implementation. And the point is that a larger number, so I can eval this perhaps, and I can also eval this. Okay, have I got the order wrong here? Right, this times this. This is a 7-digit number, and this is like a 9-digit number or an 8-digit number. So this one is actually larger. Actually, it might be that I'm confusing the thing that I'm supposed to be doing. The thing it's like, is it supposed to be LCM n here? Because this would be sensible. Yeah, so I think this is likely the theorem that I was supposed to prove. So it might be LCM m. Now to counterexample, actually. Okay, what's the counterexample? N equals 2, m equals 1. And is this supposed to be like n instead of the other one? Okay, let me see if I can like reconstruct the logic for why this was supposed to be the case. So I have x to the m minus 1, and I have 1 minus x to the n minus m, right? So the point is this thing, from this it follows that like you can do multiple decompositions, right? So I can do this sum. So basically one way of writing this is to take this and like binomial coefficient out the sum. So this is times the sum from k equals 0 to n minus m of n minus m choose k. This is a weird way of writing it. Times x to minus x to the k. No, this is not right. Is this right? Just a sec. It's like, look up the binomial formula. Binomial theorem. Right. X plus y to the n is the sum from k equals 0 to n of n choose k, x to the, so in this case, x is 1, and that gets ignored, and y is negative 1, or y is negative x. So yeah, that's actually right, to the k. Yeah, that's great. And the point is that you can actually factor out this negative 1, I think. So another way of writing this is like negative 1 to the k. And then I think you can sort of like manipulate this. You can take the sum outside. Yeah, so we can like take the sum outside here. Then this expression can be like evaluated because this is just some integral from 0 to 1 of this thing, right? And so right, I can select this, and this it becomes m plus k minus 1. And so the integral of this, right, so the integral of just this would be it would be x to the m plus k without the minus 1 times a factor of 1 over m plus k. So like another way of writing this is to say, I guess the point is that we can actually extract all of this because none of this depends on x. That can go all out here. And then the point is that this can be like the difference from 0 to 1 of n plus k, frac 1 over n plus k. Okay, clearly this is not amenable to writing LaTeX, but that's fine. And the point is that this is then equal to, right, so if this is going from 0 to 1, then the x goes from 0 to 1, and so we really just get 1 over n plus k. And so that is one way of computing this. And then we also have another formula based on the beta integral. There's another much cleaner formula, which I think is obtained by integration, but I think we have a theorem in MATLAB for it, which is this one, right? So, okay, so I have to be careful here, right? So the real values are greater than 1, I guess. But the point is that it's gamma s times gamma t equals gamma s plus t. Or so like this is the other thing we have. So we have already in MATLAB that this is true. Okay, so I can also rework. So I have to like make sure that I'm writing the right thing here. So with s and t as u and v, here I should just duplicate this line. The other alternative thing I can write is I can say, okay, this is cool, but with u, this is s and t, and so we can now reformulate this here. So like basically, so setting m minus 1 equals s minus 1 and n minus m equals t minus 1, we get, so s is that, t minus 1, just a second. Right, so m is equal to s, t is equal to n minus m plus 1. The sum of those two things is this, and I think this is what we have here, right? This integral from 0 to 1 of x to the m minus 1 and 1 minus x to the n minus m, right? And we can like rearrange this to get something cleaner. We can take this, just divide it by that, and we can even like rewrite this in terms of a binomial coefficient. Right, yeah, so the gamma function can be rewritten as m minus 1 and n minus m over n, and this can be rewritten as this, right? Let me just double check here, right? The point is that we have n minus 1, so let me just think about this, right? If we multiply both the top and the bottom by m, okay, no, wait, what am I, yeah, m minus 1 factorial is equal to m factorial divided by m. And so what we have is 1 over n choose m times 1 over n, right? Okay, great. And so I guess the whole point of this is that this is a sum from k equals 0 to n minus m, right? So if k is at most n minus m here, we have 1 over n. And so so this basically, the denominator is a number which is at most n. So the point is that the integral times LCM n is, I guess, the thing that we're working with here is an integer. Or here, let me like write like what this beta integral is in particular. So I guess the beta integral that we're working with, beta integral s and t. So it's the beta integral. So I worked it out. It's the beta integral where s is equal to m, right? So this is equals this. This is the beta integral of where s is equal to m and t is equal to n minus m plus 1. Yeah. And I've just this is just a copy of exactly what's there, right? So this is basically two ways of rewriting the beta integral with m and with n minus m plus 1. Yeah, great. So fact number 1 is that beta integral times LCM n is an integer, or put another way, what we have is that, okay, so this times this is an integer, which means that it's a positive integer. I guess another way of saying this is that this is a positive integer, which should be clear because we're integrating a positive function. So this is times n is a positive integer. It's at least 1. And so LCM is greater than 1 over beta integral m times n minus m plus 1. I guess the point is that it's a little confusing because I can multiply two rational numbers together and get an integer. But that doesn't necessarily mean that the inverse is an integer. It could just be that its inverse is not an integer. Maybe I could talk about the denominator of that, but okay. I guess the point is that there's maybe not necessarily a clean way of writing it like this. Except that there is, right? Because, okay, so clearly it is like the inverse of an integer, right? Okay. What have we achieved? These are not so, and okay, just to clarify again, this is exactly the same expression that I have up here, right? So what I can also write is this. So the beta integral is this. So the beta integral is just 1 over this, right? And so what does all of this tell us? This tells us the beta integral m times the LCM n is a positive integer. So since this, and to write it more suggestively, I think I should write it m times this. And the other thing that I'm going to write here is that this is the thing. So LCM n is a positive integer, m times n choose n is a positive integer. So this is a positive integer. We get that m times n choose m divides LCM n. Okay, so let me try and rewrite this. Okay, so clearly I had this wrong. This is supposed to be an m, and this is supposed to be an n. Gave up after failing to generate values that fulfill the preconditions. Okay, and clearly plausible is working because when I gave it some bogus thing where this was like 3, right? It finds a counterexample. So clearly plausible is smart enough to like be calculating things here, but it's also failing to generate values that fulfill the preconditions 1 times. This is just such a confusing error message because it makes it seem like it wasn't able to find an m and an n value that are right, but it seems like it's doing it perfectly fine. It seems like it's working. So I think this is the correct theorem. So basically, this is the theorem that I'm supposed to be proving. That this divides this LCM thing. And the point is that, okay, so to go further, we can now use this fact. Use this fact to prove that that this is true. And the reason that we can do this is basically we choose some particular values, like we can set m equals n in the above, and then we get this. Sorry, n should be like n is equal to 2m, right? And what we get from that is that this holds true. Okay, clearly it's not very good. Can set n be equal to 2m. Okay, clearly I have to write something coherent if the AI is going to get it right. And what we get from that is that m times 2n choose n is a divisor of LCM 2n. And then I think the other thing that we do is we do it with can also use m plus 1 and like 2n plus 1 to get this. And like basically between these two facts, we can like compute some very nice divisor of LCM 2m plus 1, which is like pretty large. And that's enough to like complete the lower bound. Okay, so let me see if I can proceed to carry out this proof here. Okay, so the first thing to note is that so the critical value of the beta integral. So like let b equal beta integral of m and n minus 1. Okay, unknown identifier, your beta integral. What? Okay, clearly I need to open complex. Or maybe I should just, it's a little annoying that it, like the complex, I'm not really interested in the complex namespace because all of these facts are going to be facts about natural numbers really. So I'm just going to do it like this. So let B be this. B is a complex number. So now there are two facts. We have that B is equal to, B is equal to this, right? Sorry, I think that's fine, right? This is the first, this is the second one here, which is this should be relatively easy to prove. And then the other thing we have is that B, or I guess we'll call it BEQ prime, BEQ prime colon B. B is equal to, okay, that's not what I want. What I want for the second one is I want this sum here. Okay, I don't need the dx here. Yeah, so I don't want anything involving a bunch of gammas. What I want is that this is equal to the sum for k. I don't know why it's so bad at knowing that \n is the thing that I want. The sum for k equals 0. Okay, k equals 0 to n minus m. So maybe ICC is a more appropriate thing. ICC from 0 to n minus m. I guess it was doing it right. And I guess this makes sense. N minus m plus 1, right? That gives me the sum from k equals 0 to k equals n minus m. Okay, so it had it right. B is equal to the sum for all k in this range of -1 times n minus m choose k times 1 over m plus k. That is what I have up there. And so these are the two critical facts that are supposed to be true. And from these, basically the rest of the proof is going to go something like rewrite B prime, rewrite B prime at B eq. And so I get this fact, and I guess, okay, maybe a cleaner way of writing it. Okay, so B is actually a complex number. Maybe I want it to be a rational number. Okay, let me rethink how I'm writing this. B is a complex number if I define it this way, but a much better way of having it be would be to have it be to have B be a rational number so that it's closer to what I'm about to have happen to me in another way. Of course, I don't want to divide by this. So fact number 1 is that B is equal to this complex integral. Yeah, so this is better. Fact number 1 is that B is equal to this beta integral. Fact number 2 is that the complex beta integral is this. We rewrite BEQ at BEQ. That gives us that B, this rational number B, is at this, has this sort of sum property. Yes, as cast to complex numbers. And now I want to get rid of that casting somehow. Are these all cast to complex numbers? They're cast to real numbers in here. Ideally, they would be cast to rational numbers. So maybe one way I can do that is to change this to a Q. And now I think they're all rational numbers in here. Yeah, rational numbers. So we have this. And the point is that, okay, this is all very well and good. There's probably some cleaner way that I can say this. Like right at this point we haven't proven that 1 over b is an integer, but the point is that 1 over b is an integer. So the ultimate thing that we are trying to prove from all of this is that, yeah, like, okay, so what happens if I like start unwrapping things? Like, I always forget how you unfold the divisibility definition. Like, basically, what I want to say is that LCM. The thing is, it suffices to prove that, yeah, this is not a great way of writing it. It suffices to prove that 1 over this times LCM n suffices to prove that there exists a natural number, which I cannot name n because I already know. So there exists an x, which is a natural number, such that x is equal to this. I don't even know what this proof is. And so at this point, I'm trying to prove this. I don't know if this is like a clean way of writing this. So I have B, right? So I go all the way here. I'm trying to prove I have b equals this. B is defined to be this. Right, I've rewritten with b, so I can now clear b prime. And the point, okay, so this is still cast to a c. How do I, rat.cast, rat.cast. So clearly, okay, so I just know that if I write out the thing that I want, the thing that I want is, okay, what I want is that I want this in terms of rational numbers, not these other weird numbers. So what I want is that, sorry, I'll comment this out so that I can actually see what I'm doing. Yes, b, which is equal to this. This is a, what I want to have is that this rational number, the point is that this is an integer. So there's some theorem. The point is that, it's sort of, right, we have like is, for real numbers we have is rational. I wish there were like predicates about when, I wish there were like named predicates about when particular rational numbers are integers and things like that. So I don't know what the cleanest way of writing this is. But if I have, the point is that if I have this times LCM n, this is what I get. Right. The point is I obtain and I use x, probably use x. X is a natural. Are these naturals? These are naturals, right? Use x. Can I like push cast? Is it push cast? Push cast at hx? Okay, maybe what I want to do is queify the rest of it. So can I queify unknown tactic? Really? What the hell is this? Panic. Okay, well, this is concerning. Zeify? Is Zeify an unknown tactic? I really thought that there was a tactic called queify. All tactics. There's really nothing called queify to change things into... What do I have to import to get this? All right. Used to shift propositions from n or z to q. Yeah, okay. So clearly I need to... Okay, I made this shortcut. Enter queify. And this will tell me what file it's in. MATLAB tactic queify. Let me see if this works. Import. MATLAB tactic queify. Okay. And now can I write queify and have things work? Yeah. Rewrite hx. Simp. Ring. Field simp, maybe. No goals. Great. Cool. Wait, unsolved goals? Am I insane? Okay. Am I missing something here? I have, these things are positive, right? I guess that's the thing that I'm missing. Right. Yeah, so have that q is not equal 0, have this is not equal 0 by trying to prove it. Sorry, I don't know what's going on. Build simp this. Yeah, okay, well, I have this twice, but no goals, right? And this should be, okay, so this should just be some lemma about this. Is it even true that m can't be like 0 here? If m is 0, then, okay, let me just work this out. If m is exactly equal to 0, I guess it's not true because in that case, we have 0 on this side. Okay, so m does need to be at least 1. Okay, interesting. But this, sorry, should be pretty trivial. The point is that this should like simplify or something. Does this simplify? Choose not equal to 0. I feel like there should be something about, if I go to Lugal, no, sorry, I want to go Lugal, please, just take me there. I want like nat.choose 0 something. Choose equals 0 if, right, okay, could this be like a simp lemma? It would seem like this should be a simp lemma, right? N choose k is equal to 0 if and only if n is less than k. Yeah, I feel that this should be a simp lemma really, but yeah, so I mean I can do this now, but simp this exact something dot left should be simp lemma. Exact could not close the goal. Really? Like, how do I like exact h dot left or h dot right? Is it not exactly this? Isn't it exact supposed to solve it? Exact. You can't close the goal even when it's just a disjunction or a conjunction. That's a little weird. Okay. To do. Okay, but that works. Okay, so I don't even know if this like suffices statement. Am I going to need this? But the point is that there exists an x such that this is this times this. Okay. Right. Okay, so proceeding forward, let B be this. Okay, maybe it's better not to do the let statement, so I'm just gonna like close this off. I'm gonna write this, right? So I get all this, and apparently, am I in, is the issue that I'm in complex numbers at the end? Yeah, this is not what I wanted. The thing that I wanted, these are complex numbers. These are not complex numbers. The statement I wanted was this, but not with complex numbers, but rational numbers. So let me see if I can obtain that. Yeah. The point is that some point after here, I want to say have this. This should be a rational number. Sorry. I have a whole bunch of up arrows in here. Failed to synthesize something. Okay, can you be a rational number 2 maybe? This line exceeds the length limit, but I don't care. Great. Okay. This is the thing I wanted, I think, right? So this is this. The point is that I can rewrite this. I can just rewrite this where I am, where I sit. And the point is that all of these numbers are integers. We have a sum over a set of integers. Yes. It feels like there should be, it feels like if I go to Lugal, did I have Lugal here somewhere? Lugal. Yeah, so what was I looking for? The point is, I feel like there should be, I at least want the claim that if I have a sum of things which are, what I really want is exists x in a set of integers such that like q a rational is equal to x. But this is not well formed. Oh, excuse me. Like is integer. Rational dot is integer. Is integer. Do I have this? What is this? Localization. We're starting to get into terms like localization, which are like high level math terms. Is in the image of R. Yes. Okay. So that's close to what I want, right? Is localization. Ugh, what is an is localization? Is integer. Yeah, this is sort of what I want, right? But I don't like, there's an algebra from the ring to S. It's in the image of the localization map. Design overview. Reason up to my isomorphism. Localization map. Reinstantiate the algebra structure. Okay, this is all very nice. I think, yeah, so what to do? The point is that the reason that there exists a natural such that this is the case, in fact, it's even a little inconvenient that this is a natural number because the point being that some of these things are negative, right? It's not like totally obvious that this is positive, except for the fact that the thing that we got at the end is positive. Right. So like the point is that in fact we should be able to say something like this is an integer, and we obtain this. And the fact is that x is positive. Isn't there something like, okay, going back to Lugal again, there should be something that is like, okay, so I simply want from z to n int to nat. Yeah, so something like this actually. Maybe even better would be, what happens, where did my Lugal window go? How do I navigate back in Firefox? Yeah, maybe int.natabs would be better. Okay, .natabs. Okay, without the int though. So if I qify this, I guess one point is that if I qify this, now all of these things are here. This is now a q. The other like fact that I want is okay, so I can rewrite hx. Yeah, so what I have is that the x.natabs, okay, none of this is correct, but x.natabs is equal to x as cast to a q. Sorry. And this is just because it's positive. And now I can maybe do this. Where am I supposed to rewrite it? X to z becomes a q, and then x is a z. So if I take this as a Q, and I write the little bars around it. Does that yeah, rewrite this X. I comment that out and the rest of the proof works. So the point is that, so yeah, so now I only have to prove X is non-zero, and here I can probably Qify and rewrite X. Maybe this? No, rewrite HX. And this should be resolved by like positivity. Great, yeah. Okay, so now I only have to prove that it's an integer, right? Wonderful. Much less complicated. So I have to prove that this is an integer, and the point is, right, so I have to prove this. Where am I? Yeah, I have to prove this basically using b equals. So after I've done this, the point is now I have this, and I have to prove that there exists an integer such that this is the case. And the basic idea is that it's an integer because it's a sum of all of these things, all of which are integers, or all of which, more precisely, there exists an integer that casts to them. So that is like the theorem I want. But it's one of these things where I don't know like what the proper name of the theorem is. It's like lemma. A sum of integer rationals is an integer. Is an integer. Okay. Sum of integer rationals is an integer. What could be a? So if I have, and the thing is, no, I don't want a list. What I want is a fin set S, a fin set of, it doesn't matter, index types for all I and S, mem, f of I in Z. Fail to synthesize. Yeah, no. So this is not quite right. Membership Q. Because this doesn't make any sense. I can't be like this. The point is that for all I and S, there exists an X of type Z such that X equals f of I. And the point is that if all of that is true, then it should be the case that sum of m by, sorry. And of course I have to take the sum using this. And then identifier I, can I just do like, this is iota, it's just the type. Declaration uses sorry, yeah, okay, so this is the fact that I want. Does it exist somewhere exact? Maybe? I could not close goal. This is the fact that I want, but I assume it must exist somewhere. Yeah, let me like try and do more searching for it. So there exists. The problem is I don't even know if this works. Is it possible to like do these complicated exist statements in Lugal? Not exactly sure. Something equals something else. This is not gonna work. There's too many things here. One of these things should be a rational number, so I'm like that. There exists a Z such that that is the case. What if I switch around the sides? So like there's a rational such that something is equal to it. Okay, interestingly, it works the same either way. Okay, because obviously this is a rational, yeah. Like what happens if I click on this particular definition? Arm value is discrete. Yeah, no. Okay, I mean, the lack of this makes me think, okay, maybe I have to read this. Localizations of commutative rings. Some is I don't like really want to read all of this thing. Like localization is integer. It's in the image of R. The image of R. Algebra from R to S. Is localization. Okay. Maybe I can like proceed on the theory that this is the thing that I want. So algebra from R to S. Okay, let me try this. Lemma, his localization is integer. Lemma foo, his localization is integer. I'm talking about the ring of integers into one, like 37. The rational number. Unknown constant is localization is integer. Where is this defined? Ring theory, localization integer. Okay, maybe I can import this. And it might take some time to import because who knows. Okay, no, that's great. Algebra map ZQ. Now use 27. Okay, algebra map ZQ. This seems reasonable, right? Is integer ZQ. I think this is the predicate I want. So maybe this is the right way of saying that a particular rational is an integer. It's using this is localization statement. The thing is, it's just like, why do I have to like, what is a localization? What I want to know is like, I have an algebra from R to S, and I want to know if a particular S has a preimage. I don't know what a localization is. I know what an embedding of one ring in another is. What is an algebra? Is an algebra just a isomorphism equipped with a map into its center? With a map, okay, so yeah, it is like a extends as small algebra maps. Yeah, so it has the ring morphism. So it is what I want. So is integer, it really is what I want. Okay. Oh, the question is, can I rewrite all of the things that I've already written in terms of this? Like here's something like lemma. A rational is an integer if there exists an integer. Yeah, so rational dot is integer. Rational dot is integer of exists integer. So yeah, no. The point is that for any q, a rational number, it is a fact that q that that this thing applied to q, if and only if there exists a c such like this. Unexpected token. What? Oh, I need to put a colon here. Sorry. And is there an exact? Yes, eq to if REFL. So some complicated REFL thing. So like, yeah, it's just a REFL. So in some sense, like behind the scenes, if I dig down deep enough, it's just exactly this. Okay, so I've already proven this. Rational is integer of exists integer. So it suffices to prove this. Yeah, great. And the question is, can I now do this in reverse? Like, okay, so if I'm wanting to actually like use this, I want to rewrite backwards with this. So now I just have to prove that this thing is an integer. And now here's another theorem, right? I want to know that a sum of, it follows, okay. Well, first of all, I need to, first what I definitely need to do is I need to put the multiplication inside the sum. So I want to do rewrite, I think that's inset dot sum mul. Yeah, did that accomplish what I needed? Yeah, great. And so now is integer. What I want there to be is I want there to be a theorem which says that if I'm taking an integer, if I'm asking if a particular sum is an integer, that is true. It follows from each individual element being an integer. Okay, I'm just going to keep that lemma here for now. Maybe it's possible to golf it away, but so here is another theorem. A sum of is integer, an integer rational. Okay. Okay, and it's written in the way that I did not want it to be written, because I would prefer it to just keep it. Can we, for all things is an integer? I brought this, yeah, okay. And the conclusion is that that's an integer. Okay, but so sorry, I'm rewriting this lemma here. The question that I want to know here is, does this have an exact? Not close the goal. Isn't there like, here's like where I apply refine rational is integer of exists integer. That's just the thing that I have up here. So that's not exactly what I want to do. And my last chance is like hint, because hint sometimes knows how to prove things, but it has not proven this in this case. So, sorry. Yeah, you would think that there would be something around here, right? Let me explore a bit more. Let me do Lugal with this and also searching for sums. So Lugal, I want this declaration, and I also want something along the lines of sum. His localization is integer. What did I mistype? Oh, it just didn't find anything with the sum. Yeah. Okay, but we have what we do have is this theorem, right? So it should be pretty trivial yeah, by induction. Let's try using induction. Unknown tactic. Induction S. Unknown tactic. What are you talking about? Alternative empty has not been provided. Okay, cool. Explicit pattern match. Great. By exact. Not close the goal. Simplify. Solve goals. Exact. Integer 0. Here we will also sum only. Is integer I in insert. Right. This is another place where it would be more convenient if I were talking about multisets, right? Yeah, I don't know if I really like understood the whole debate over whether it's better to have multisets be summed over, right? If it were like a multiset that are summing over, it would just be sum over this, and it would instantly decompose into an addition, and then the inductive hypothesis would kick in. Okay, I think I'm pretty like confident about this theorem, so I'm just going to leave it as sorry for now. Unsolved goals. Why are there unsolved goals? Didn't I say sorry? Why? Decidable eq I. Okay. Well, if decidable eq is something I need, then I'll stick it in there. Okay. So now I simply want to apply this theorem at the end. So I'm here. Now I want to apply this theorem. Okay, wonderful. Success. Introduce. And the point is that this is in fact an integer. Okay, so like the other thing that I want to do here, clearly I need some like API about LCM n, right? The point is that, yes. Okay, so yes, the least common multiple is in fact the least of the common multiples. So here's a theorem about that. So this is the LCM that I defined, and what I want to say is that lemma LCM divid. This is true, but not what I wanted. If I have n and m, let's not confuse ourselves. Let's call them a and b, and a, h, a, b, a is less than b, b. Then, okay, that's true, but in fact, this is also true. Sorry. The least common multiple, right? And I could say something like lemma LCM least common multiple. Yeah, so like the thing that I want to say is something like for any a and n is least of the set of n's such that all n less than or equal to a, yeah, sorry, and probably a needs to be at least 1 or something. Yeah. I'm just going to put in HA, 1 less than A, 1 LEA, just to double check that. Is plausible good enough to check this, I wonder? Plausible. Found a counterexample. Oh no. So it's saying that this is not true for 1. All m less than or equal to A. M, well, it's n. Yeah, so clearly what we also need is 0 less than m implies this. What is plausible? Issue does not hold. What is the issue? If A is 1, then the LCM of A, what the heck? Oh, it's because I have this massive comment here, and that's why it thinks it's the documentation. This function is the LCM of the first n natural numbers. Positive natural numbers. Great. Unexpected token. The issue is that I need to do something like this in order to make it a module docstring. Okay, but it's saying that there's a counterexample. A is equal to 1. 1 is less than 1. True. For all m less than or equal to 1, if it's greater than 0, n is a multiple of m. I really don't get what the issue is here. Like LCM 1 should be 1. LCM 1 should be 1. For all m less than or equal to 1, issue ... does not hold. Is least. Have I got that? The least element of a set, right? So if I've ordered set, this is a, okay, maybe the issue is that plausible should not even be capable of figuring this out, because how could plausible, like the point is that plausible needs to compute things. So this is actually an infinite set, right? So I don't know how plausible is supposed to have done that. I'm going to leave this as sorry. But it's true that it divides that everything. Okay, technically this should be like divid LCM. Okay, what is your counterexample? Ah, wonderful. This is a place where a counterexample happens. So HA, I'm claiming that it is true if I take 1 less than or equal to A. Gave up. Okay, cool. So it does not seem to find any issues there. All right, so what was the point of all of this? Yeah, the point is, yeah, I don't know the least common multiple. I don't actually know for the, right, yes. Because actually we're lower bounding the least common multiple. So in fact, we don't actually have to prove that the least common multiple is the least common multiple. What we just have to prove is that any common multiple is sufficiently large. So actually this like part of the theorem is probably not going to be needed. So we can delete that. Great. So continuing on. So we're here, localization is integer. So we want to prove that this is always an integer. And the way that we're going to prove that is that we want to get this all in the form of where the LCM n is divided by m plus k. Because the point is that this is less than n. And so therefore, this product is an integer. So what we want to do is we want to rewrite Molesok. And that gives us something where we have this, and this, and this. Great. So now we want to apply, I think mul is integer mul. So now we have two goals. The first one should not be hard. The second one, so for both of them, yeah. So for this one, we want to apply again this fact. Apply is integer pal, perhaps? Yeah, I don't know. Negative 1 to the k is an integer. Sorry. I'll prove you later. Sorry. Those to be solved. The point is that this is an integer. The point is that this is an integer. So this is a rational. LCM has been cast to a rational. This is that. Yes. Point is that, yeah. Probably like doing all this weird passing back and forth between localization is integer and divisibility of like fractions in Q. So that's a little not ideal probably. But the point, yeah. So the point is that lemma is integer LCM one divid, this is technically the exact thing that I need, is integer one divid mul LCM, and so the point is that even this is not going to be exactly right. What do I need? The point is that this is like this, but unfortunately I have a sum of two rationals here. Yeah, so I have a sum of two rationals, which is itself a rational number. And the point is that if it's an integer, yeah, okay. So I could say something like, yeah, this is not going to be the most effective way of writing that, but the point is that if I have a rational, let's say, and B a natural, and I want it to be like 1 over a rational, or I guess not. Yeah, it's fine if I do it like this. A is a rational, B is a Q, A is an integer, so HA is integer, yeah, and the point is, okay, that's not what I have down here. The point is just that it's some, divide by that. So the point is that if I have 1 over A, yeah, A is an integer, it's less than B, less than or equal to B, so I'm taking that, then this is an integer, because it's great. Yeah, it's just rewriting the divisibility. So this is the thing I think we want to prove, and I can just apply this perhaps. Oh, apply has two P's, unsolved goals. Okay, but the apply was successful, wonderful. So now we just have to do all these other facts, which follow from a range of things. So K is in finset.range of this. Yeah, yes. This is where I expect grind to be helpful, perhaps. Can grind solve it? No, grind was not able to solve. The point is that this sort of follows from this. Can I simp at HK and then at HK? Yeah, we're so close. Yeah. Okay, further. These are all nats being cast to M's. I feel like isn't there exact mod cast, no goals. Did that finish it? That's weird if that finished it. It must be surrounded by parentheses. What the heck? Okay, it's annoying. Let's use localization as integer. Yeah, I just want to say sorry about this one. Okay, invalid occurrence of dot notation. Okay, but this is really annoying because, okay, and why is it panicking? I've never seen this weird panic issue before. Huh. Yeah, that's just some concerning thing. I don't know what is going on. under the hood. Like, what happens if I don't focus the goals? Invalid occurrence. Okay, cool. Can I say sorry here? How many goals do I have left here? One goal. So I just need to prove that. So can I like apply? But I'm not going to have, so now I need to apply something like add unknown identifier. Okay, how am I supposed to use this? And close the goal with exact. Unsolved goals. Okay, 2 goals. What I simply want, this is M, this is a Q. What I simply want is to turn this into a statement about the underlying naturals. I want to like unQify, but I don't think there's a tactic for that. Yeah, of course, M. I could Qify at HK and H here. Qify at HK, Qify H, HK, Qify at H. Now can I grind, for example? Grind, failed. Okay, but like I have everything that I should need, right? M plus K is less than or equal to N, right? K is less than this plus 1. So M plus K is less than N plus 1. In other words, it is less than or equal to M. Yeah, that is exactly this. And then this should come from the fact that M is at least 1. Split. How do I split? Constructor. Sorry. Okay, no, sorry, I didn't want to copy that. What I want here is just solve it. Literith. Q, and that should work twice, right? No, why does it not work here? The issue is that this doesn't work. Man, with integers it makes sense, but with rational numbers it doesn't work. Shoot. Before I do HK, simple HK, replace HK. Yeah, by Literith. Qify. Now it should be good to Literith. Yeah, great. Okay. And then there is another goal. Wonderful. So maybe if I indent all of these and do sorry. So what do I have to prove here? Here I have to prove this. And I wanted to use this. Is that? Yeah. Right. I feel like there should be something that proves this. Exact. Exact could not close the goal. Localization is integer. I have a natural number being cast to a queue. Yeah. Okay. So that's an obvious fact. So let me prove that. Lemma. Yeah. Rational dot is an integer of nat. So if I have n, a nat, then if I cast n to a queue, then it is an integer. This is true. By use n form cast. Yeah, great. Try this. Exact. No goals resolved. Wonderful. Okay, cool. That finishes that. Okay, let's start going back up through these sorries and proving those. So, okay, so yeah, we haven't proven the most hard one, which is this. Yeah, so there's what they have mul, but they don't have pow. Is integer pow. Yeah, this is annoying. I feel like we should just have this exact theorem. Yeah, so it's just a statement that it's in the range. Wonderful. Is integer. It's just awkward that for rationals, I'm going to have to write to write that a rational is an integer, I have to actually say the type integer, which is sort of funny. Are there any other subrings of the rationals? I guess the dyadic rationals technically. Okay. Yeah. Okay. So is integer pow is a fact. Maybe I should just write that here. Theorem is integer pow. I have a, which is an integer. I have n, I induction, with 0, exact, simp colon exact is integer 1, simp colon exact, simp made no progress. Why did simp make no progress? Simp pow suck. Yeah, clearly. So that makes sense. Simp is integer mul. Integer. Okay. Clearly, I should be rewriting this. I should be applying is integer mul. So I should rewrite this. I should apply this. We can figure out later what everything is. Exact question mark copy or line copy paste exact HA. Yes, but I was going to fix that. Does it really not work if The following tactic starts with, yeah, okay, but this kills, this is super annoying. It kills the ability to click on it. I was going to fix it immediately, but the linter, yeah, this is wonderful. I should file like an issue or something. Let me file an issue. Issue. New issue. And the issue is that the multi-goal linter prevents exact question mark from making clickable clickable whatever. Oh no, I'm just wrong. I just need to click this. Okay. This is actually not worth filing an issue. Wonderful. Delete that. Okay, and now I can do, what do I do here? Show term. Is integer mul. This is so weird. I feel like I had this. I don't know what the issue is. Okay, is integer pal. Great. And it has a whole bunch of things here. Is integer, yeah. Maybe I will just copy all of these over into here so that I can have it in the same file. Wonderful. If I do all of this, and I just write here at the top of the file some statement type is integer. What do I have? Is open is localization in this. Okay, cool, wonderful. Unexpected end of, okay, so I need 11 down there, but that's fine. Okay, so all of that is fine. Where was I? The point is that this should now be resolved by an exact, which I will now test. Apparently it is not. This is a rational, okay. Yeah, clearly it's not resolved by an exact, but it should be resolved by an apply. Okay, if I type apply question mark, will it find the thing that I have? Yeah, it did. Wonderful. And here, can I do exact? Okay, the other thing that I should clearly have is a sub version. So, let's make another theorem, or a neg version. Is integer neg. So if R, S, all of these facts, I don't need N. I have A as an integer. I don't even need this. I want to say this. Com semi-ring. Okay, com ring, maybe. Com ring, sorry. Like exact. Have a, yep, by ring, rewrite this, apply as integer mul. Okay, but that doesn't tell me how to do this. Okay, so, okay, yes, I'm being very dumb and I've just gone in circles. So what is actually, okay, what is the way of proving this? Is integer. Maybe, okay, maybe the point is that it's not true because I could be doing this all with n. There's an algebra from n to q, and technically I am that's just not working at all. Okay, so clearly this is just not true, I guess. If it's com ring, it should be true. Okay, let me focus back on the goal that it was when I had it. Use -1, exact ruffle. Okay, right. Yeah, one I'm at. Sorry. Okay. Can I undo back to where I was? Yeah. Can I? Okay. Rewrite this, and now use -1. Ruffle, solve goals, ruffle failed. It's not definitionally equal to the right-hand side. Simp goals to be solved. Interesting. Okay, so we managed to prove this fact. Probably I don't even need both of these to be a com ring. I don't want to think about that right now. So, but it's also a little weird that it's not picking up. It's an integer neg. Anyway, okay, so I don't know what I'm doing wrong here, but I'm just going to use -1, simp. No goals to be solved. And this is the tricky part. Okay, finally well, not the last sorry, but the sorry. Okay, have I done something wrong here? No. This is fine. This is just, yeah, cool. Just using this is integer of nothing. Okay, cool. Where did I, where did I actually figure out that this was the case? Yeah. So I used implicitly this fact, which is what I should prove now. Well, I didn't use it implicitly. I used it explicitly probably, but whatever. So the point is that this should follow on from this. And the reason is that, okay, so I have that it's an integer. Yeah, clearly I actually probably don't need the 1 less than or equal to a in this case, because if a is equal to 0, then it just collapses to 0 and everything is fine. But okay, so is integer 1, but I don't necessarily have to worry about it because I can just proceed. So but what I probably should do, yeah, okay, it's just going to be easier if I make it look the same. Okay, so let me try this. And it'll tell me that I got something wrong here. Yeah, tactic constructor failed. Yeah, because like Linnerith, this is like a Linnerith. No goals to be solved. And this is also going to be a, it all changed. I'm just, yeah, I'm so dumb for making things look nice. Simp at HK, yeah, so that is all fine. And the issue is that something has changed here. So the point is that this is now 1 less than M plus K. And I want this to be a Linnerith. Linnerith failed to find a contradiction, but that's mainly because it doesn't know K is positive. So the point is that I should also have K K cast to a rational number is positive. Exact, and hopefully it should, okay. Neither of these worked. Wow, that's a little bit annoying. Unsolved goals. Okay, so clearly that is what's needed to solve the last goal. Why does this have an issue? Oh, it doesn't have to be like this. It has to be LE. Now that's fine, but the question is, okay, K is greater than 0, and I want to obtain H prime. I think I need like this. Ugh. And I also want to QFI. So QFI at H. Okay, now it's happy. Wonderful. Okay. Okay, so where was I? I was proving something up here, right? Yeah. This one. From basically I want to prove this one from this one. And of course it's critical that I don't apply the multiplication lemma here, because the point is that one of these is not an integer. It just divides the other one. Yeah. So have. The point is I'm going to do a have statement. I have this one. Application type mismatch. 1Q. A is not an integer. Okay, so let's proceed. Yeah. Obtain X revel A is an integer. Yeah. Okay. X HX, let's say. Do I really want to obtain it, or do I just want to have it? This is annoying. What I want to do maybe is rewrite using didn't I like prove some lemma about like existing an integer? Is integer of exists integer. Yeah, sure. So let's take these, move them above here, and rewrite. Let's do rewrite actually. So let's rewrite at, okay, now I can obtain, yeah, great. Okay, so what have I accomplished? I have X, the integer. Of course, X is equal to A. All of these things are equal. So X is in fact a natural. So X is a natural. So what I want to do is something like, yeah, so there's a natural which is equal to X, and there's yet another thing to add to there exists, exists natural. I think previously I was just doing like the absolute value or something. Basically, I just want to use, okay, let me think about this. I have X, which is this Z thing, and that's equal to A. So I just want to use LCM B X dot abs dot net abs. So use, can I please use? Actually, okay, I'm just proving it's an integer, so I don't need necessarily anything else. What am I using? I'm using LCM B over X. Yeah. Use LCM B over X. And so now I have to prove that this is true. Simplify and get me anywhere. Okay, so I'm casting things. Subst hx field simp. Have X is not equal to 0. Sorry. What is this? This is X cast to a rational, and this is X cast to a rational. Wait, these are the same, right? X, okay, maybe I need to QFI first, because this is an integer. Oh shoot, we're doing integer division. That's not good. Yeah, so if we're doing integer division, there's a possibility of truncation. That's not necessarily what we want. Yeah, the issue is that that's what's happening. So I don't know how to avoid that necessarily. Yeah. Clearly we could QFI push cast, but I can't push it through here because it doesn't know, like I'm casting it to a rational, but it doesn't know that this divides this. That's the issue. HA. Clearly, the whole point was to find a natural, right? So yeah, okay. So at some point I have to do this, right? The point is that x, this integer, divides LCM B. Yeah, can QFI do that? That's an interesting question. So like, if I say I have that x as I think an integer divides LCM B, it'll cast that. Who even knows? But so this is where I have to prove that. But now I have this, and now so I have this statement, and we have this. So that looks like that. That looks like that. Can now I do QFI using this? Yeah, wonderful. Okay, cool. And now can I field simp? Field simp. No goals. Cool. And I think is this even needed? Yeah. So I guess that is not even needed. So I can just finish it off with the key simp. Okay, cool. So now all I need to do is this. Yeah. So this is where I want to do I want to do my have statement with okay, but HA is still not right. So yeah, HA, 1 is less than this thing. Okay, yeah, so what I have is, I have that, what it has to be, I have that 1 is less than or equal to x dot nat abs by, sorry. So this is true. I'm going to use this, that, okay, more annoying things. I have x.natabs is less than b. Have this too. Natabs is less than or equal to b. I'm sorry. This is this too. Sorry, I need to type my things right. Unexpected token, expected command. Why did you expect? Yes, it's like this. Have this. And now the point is that, okay, so I have these integers. Yeah, so yeah, this is becoming very cluttered, but the point is that I can now say obtain C this from this, use C, rewrite HC maybe, push cast, absolute value of x is equal to x, simp, or is equal 0. Can I like grind this out maybe? See, this is a case where a grind should work. Left, maybe. And it's not possible for it to QFI, and fine, that works. Okay, great. I don't necessarily need all of these written out here. Okay, cool. 1 less than or equal to natabs, x natabs, QFI. Okay, haven't I already QFI'd here? This is a Z, it's being turned into a Q. Can I just QFI normally? Can I grind here? This should follow from this. This is being cast to a Q. This is being cast to a Q. Is there nothing that knows how to prove this without having to like, no, that's annoying. Sorry. The point is that this is an obvious fact that I don't know what the name is for. Does exact not work? Exact. If A is less than something, then A is less than the absolute value of that thing. It feels like this should be obviously true, and I don't know why the automation is not finding it. This is annoying. I'm casting this integer to a Q. Yeah, it was necessary to do this. Okay, this is time to go back to Loogle and like try and actually find the statement, because this is just clearly true. So A is less than or equal to, it's sort of annoying. In Loogle, you have to do all these question marks. I don't really get why that it has to be the case. Yeah, expected no space, but if I do this, expected no space. Okay, so clearly, okay. I need to actually find the name of the theorem, the name of what is actually being applied here. It's just abs. Okay, yeah, so let's do it without the notation. Abs, question mark B. Right, yeah, so isn't it just like LE abs? And what has gone on with Firefox? Did it always have the like back button over here? Okay, copy LE abs, rewrite, left, act, yeah, okay. I don't know why that had to be so hard. And okay, so is this going to be harder? X is less than B, X is positive. Clearly it's important that 1 is greater than X. Okay, so actually we have nat abs LE something. Okay, so if I can type it correctly, it'll be something like this. And the point is that nat abs, okay, but I don't want anything on the other side. Yeah, this is Okay, so this is, yeah, this is, there's no like, I can't type like bound, for example. No progress. This is the sort of thing I feel like grind should be able to accomplish, but I don't know how to tell it what it needs to do. Um, okay. Well, perhaps it's better if I just move on and try and prove the rest of these facts. Okay, because I also have to like prove this whole fact here. Okay, this is gonna take a while. So I had this. What exactly is going on here? Just a second. Let me like pull my screen back up. Okay, hopefully that's fine now. So okay, I still have some issue here. Yeah. So let's just delete this. Okay, let's see if I can like proceed with like further facts about this rather than like spending all my time proving trivial theorems that should really be handled by the tactics. Okay, so the point of this was I was trying to prove this. What does this follow from? Okay, this is just something I already have, right? This is basically like QFI, basically just QFI. What is going on here? This is one. Okay, I need to just convert BEQ, right? Convert BEQ. I return B, definitely equal. Similar to refine, right? But is it, why can't you even do a single, okay. This is a Q. This is a C. Ah, yes. Okay, I see the issue. Is there a CFI tactic? We have an RFI, we have a QFI, but do we have a CFI? That is an interesting question. Let me just type in CFI and see if it works. Yeah, no. Right, so this is just a C, and this is just a C. Can I not like exact close goal? I know I'm so close to proving this. It shouldn't take me like 5 minutes to prove some triviality like this, but I guess that's how it is. Okay, so what is the theorem that says that if I go from um, from Q to C, right? The point is just that this is true. If I cast, yeah. What is this? This is just a Q, right? So this is going from rat cast. What is this? This is a Q. Yeah. Okay. So, I mean, in some sense, it's unfortunate that it's like this because what I want it to be like, what I want BEQ to really be like is like this whole thing, but I don't want it. Here's like, how do I say? I just want it to be. I don't want you to push the C through, right? Do I like surround it with another and like say like definitely stick it just as a Q, right? So this is just a C casting, and now it still doesn't work. But now it's more confusing why it doesn't work because surely this is just a Q. Okay. Is there not a theorem like theorem? If I have two Qs, theorem foo. If I have A and B, they are rational numbers, and it should be the case that A cast to a complex number equals B cast to a complex number. That implies A equals B. Ooh, true, exact. Is there no theorem about this? Yeah, there should be like very frustrating that it can't find like a theorem to do this. What could be? How do I find this? Like, does hint help? Symbol only. Okay, so that solves it. Okay, wonderful. We found it. Like, apparently that doesn't work. So why doesn't rat.castin like NP? Why does that not work? I don't get why exact doesn't work here. That equals that, then that equals that. So I just have to write this apparently. Rewrite this at BQ. Convert BQ. Solved. Wonderful. In fact, this should be an exact. Wonderful. Okay, so that proves that. And so now I'm back here, and this is fine. I can restore it to what it was before by just doing like push cast, presumably. So this is a C, and this is the beta integral. Okay, so what? Yeah, this is the fact that already existed in MATLAB, so I should be able to use this. So let me go into the beta integral, the function that, or the file that talks about beta integral. It's just one of these ones. So this, yeah, so gamma mole gamma equal beta integral. Okay, so I could really get screwed here if it doesn't actually have the fact that like gamma is related to it's related to the binomial coefficient function, the choose function. But this is all that I really was supposed to need, I think. So, yeah, interesting. Gamma. Of course, these have to be positive, yeah, because otherwise we're talking about like the values that don't exist for the gamma function. Gamma function is not defined on like negative. Gamma is okay? What's the definition of the gamma function? Gamma, gamma function, right? But what is the definition with respect to the factorial function? Simple formula for the factorial is only, yeah, okay. Where's the yeah. Gamma n equals n minus 1 factorial. So when gamma is greater, that means, yeah, it means the factorial can be 0. So I think that's fine. Okay, so cool. What I really just want to write is like a factored thing, which says that the beta integral of two naturals, these are just two natural numbers, right, that have been cast. Yeah, so, yeah, okay. Let's write this as a lemma because who needs like an actual, so lemma. Complex dot beta integral, that's not what I wanted to do. If I have two m and m's, yeah. So the point is that I complex beta integral m and n, okay, let's actually do a and b. So if I simply do complex dot beta integral of a cast to c, b cast to c, that is in fact equal to, so it's equal to, okay, I can use the gamma function, right? So this is like the trivial way of saying is like gamma, is there no notation for gamma? That's sort of weird. Gamma, okay, but let's not deal with this. Gamma s times gamma t over gamma s plus t. Gamma s, gamma t over gamma s plus t. And I guess I can make these s and t too. S and t could be naturals, s and t are natural numbers. Yeah. Let's make this complex beta integral, gamma mole gamma div. Okay, mostly, screw all of this. I just want to rewrite this theorem in terms of can I just like get a theorem that, yeah, I'm just going to do the exact same complex dot gamma mole gamma beta integral that is equal to that plus times that divided by that by, has already been declared. Oh, yeah, because I didn't change it. Beta integral sorry, okay, yeah. And apparently I have to capitalize the G in gamma. This is a theorem expressing the beta integral in terms of the gamma function, like this. Cool. Like this, unknown constant. The thing that I want to rewrite with is just this very thing because I already have the gamma s times gamma t thing in there. So something like that. I can do that. I can write HSHT and field simp. Okay, only thing that needs to be proven here is that gamma s plus t is non-zero. Gamma function, is the gamma function non-zero? Like presumably, like, okay, so I know that the real parts, so I have something with positive real parts. Presumably it is. Let's see if I can massage my way. Have gamma s plus t is not equal to 0 by gamma ne 0. Okay, we'll see what that is in a minute. And then we can apply field simp. Okay, so gamma ne 0, gamma s, okay. The gamma function does not vanish on C except at non-positive integers. Yeah, so for all m, s plus t is not equal to negative m. Intro m, point is that it's because the real parts are like this. So we already know that the real parts, so is it possible to do like x'd? Like I have two complex numbers that are not equal. Thing that I want to do is say, the thing that I want to do is say something like, how do I, yeah, see like complex not equal if and only if the real parts are not equal or the other parts are not equal. What could be the answer? Yeah, complex. Is there something like complex not equal if? Yeah, no. Complex. How do I know if two things are equal? Okay, I just need to like write more facts. The fact of the matter is that I have that the real part of s plus t is not equal to the real part of negative m, the complex number by, sorry, I don't know how to prove that. The fact is, now, can I exact maybe? Yeah, okay, Conger R agree, I'm sure. What did I do? I put this random equal sign. And so, and this, can I like simplify this maybe? Simplify, all right. So I have that, and I want to say something like have real part of this is less than or equal to 0 by simp, sorry. And now I want to be able to say Linnerith, no goals to be solved, no goals to be solved, cool. Okay, great. So now I was able to just rewrite this in terms of this. Wonderful. I think now I am going to take a break because I've been doing this for a while. Maybe I'll come back in a few hours and try to finish this, but I think this has been enough for one sitting. How long have I been doing this? Around 2 hours or so. So this has been fun. Thanks everyone for joining, and take care. I'll try and let people know on the Zulip if I'm going to come back and do more of this.